So our basic idea is that you have the Earth's surface and you have a satellite up at geostationary orbit and you drop a cable down to the surface. And the most fundamental question you could ask about whether this is feasible is, if you did drop a cable, would it be able to support its own weight? If it can't support its own weight, there's no way it's going to be able to support carriages going up and down or anything like that. So the minimum requirement for a cable is it must be able to support its own weight. Now up near the top, it's weightless because the centrifugal force balances the gravity, but down near the bottom, it certainly won't be weightless. And so let's say we take a slice of our cable here and look at the force balance for that slice. We don't want that slice to fall down or bounce upwards. So what forces have we got? Well, there's going to be a tension from the cable below it, a tension from the cable above it, and there's going to be a weight mg downwards. Must those sum to zero? Well, no, because the whole thing is rotating. They must sum to give you the necessary centripetal force to remain in a circular motion. So what we know is the net force is going to be, well, let's set some coordinates here. Let's have distance r from the centre of the Earth, and the length of that little strip is delta r, and we'll give a cross-sectional area A for the cable. So the net force is going to be a tension force downwards minus a tension force upwards at the top, which is going to be different from the force downwards by some amount delta t. And then we've got the gravitational force mg. We have to allow for Newton's law of gravity here because g is not going to be constant over the case. So this is going to be g m of the Earth, m of the slice over r squared, and that must be equal to the necessary centripetal force, mv squared over r, but let's do it in angular frequency because the angular frequency is going to be the same all the way up and down, whereas the linear velocity is not going to be. So that's going to have to be equal to m omega squared r. Now what's the mass of this section here? Well, the mass is going to be the volume times the density. So it's going to be the density times the length times the cross-sectional area. Now the tension here and here are going to cancel out. So what we find is that the change in tension across this little length has got to be equal to g m over r squared minus m omega squared r. And if you substitute in for the mass, you find that it's equal to g m over r squared minus omega squared r times a times the density delta r. So that's telling us how much the tension must vary. By and large, the tension must increase as you go up, because the further up you go, the more cable you've got below dangling down. So the further up you go, the more tension there has to be. So the peak tension is going to be at the top up here somewhere.